So in the last episode, we had proved one important theorem as per which the derivative of sine inverse x is equal to 1 upon square root of 1 minus x square. And now in the continuation of in finding out the differential coefficient of inverse trigonometric function, in this episode we shall prove one more important theorem, and as per which if x belongs to the interval minus 1 to 1, then the differential coefficient of cos inverse x with respect to x is equal to minus 1 upon square root of 1 minus x square. Again, we know it very well that the differential coefficient of a function f of x is given by limit h approaches 0, f of x plus h minus f of x divided by h. And now in this case, f of x is equal to cos inverse x, and f of x plus h will be equal to cos inverse x plus h. So that means derivative of f of x with respect to dx is equal to limit h approaches 0 cos inverse x plus h minus cos inverse x divided by h. And if you remember, in the chapter inverse trigonometric function, you have already learnt that sine inverse x plus cos inverse x is equal to half pi. So which means cos inverse x can be also written as half pi minus sine inverse x. And that means in place of cos inverse x plus h, we can also write half pi minus sine inverse x plus h. And similarly, in place of cos inverse x, we can also write half pi minus sine inverse x. So now this derivative becomes derivative of f of x with respect to dx equal to limit h approaches 0 half pi minus sine inverse x plus h minus half pi minus sine inverse x. And now cancelling half pi in the numerator. So now we have the derivative f of x with respect to dx is equal to minus limit h approaches 0 sine inverse x plus h minus sine inverse x divided by h. And in the previous episode, we had proved that limit h approaches 0 sine inverse x plus h minus sine inverse x upon h is equal to 1 upon square root of 1 minus x square. So that means derivative of f of x with respect to x is equal to minus 1 upon square root of 1 minus x square. Or in other words, and f of x is equal to cos inverse x. So that means the derivative of cos inverse x with respect to x is equal to minus 1 upon square root of 1 minus x square. And that's what we wanted to prove. Now let's prove one more important theorem. And as per this theorem, the differentiation of tan inverse x with respect to x is equal to 1 upon 1 plus x square, or in other words, derivative of tan inverse x with respect to x is equal to 1 upon 1 plus x square. And again, the differential coefficient of any function f of x is given by derivative of f of x with respect to x equal to limit h approaches 0 f of x plus h minus f of x divided by h. And here f of x is equal to tan inverse x, and f of x plus h is equal to tan inverse x plus h. So now this differential coefficient or d of f of x with respect to dx will be equal to limit h approaches 0 tan inverse x plus h minus tan inverse x divided by h. And what's the value of tan inverse x minus tan inverse y? And remember, in the episodes on inverse trigonometric functions, we have already discussed that tan inverse x minus tan inverse y is equal to tan inverse x minus y divided by 1 plus xy. So now this limit can be also written as limit h approaches 0 tan inverse x plus h minus x divided by 1 plus x into x plus h and whole divided by h. And that simplifies to limit h approaches 0 tan inverse h upon 1 plus x into x plus h divided by h. And that simplifies to tan inverse h upon 1 plus x square plus hx whole divided by h. And now to simplify it, what we can do, in the denominator side, we shall multiply and divide the denominator by 1 plus x square plus hx. Because when we do so, then in the tan inverse side, we will have the same value in the numerator and the denominator. So now this expression becomes derivative of f of x with respect to x is equal to limit h approaches 0 tan inverse h upon 1 plus x square plus hx divided by h upon 1 plus x square plus hx into 1 upon 1 plus x square plus hx. And why we have multiplied and divided the h by 1 plus x square plus hx? Because we wanted to have the denominator in the form of h upon 1 minus x square plus hx. And why so? Because we know it very well that limit h approaches 0 tan inverse x upon x is equal to 1, and we wanted to write it in that form. So now this derivative becomes, and now this limit h approaches 0 tan inverse h upon 1 plus x square plus hx divided by h upon 1 plus x square plus hx is equal to 1. And when limit h approaches 0, then 1 plus x square plus hx will be equal to 1 plus x square. So now this derivative becomes derivative of f of x with respect to dx equal to 1 into 1 upon 1 plus x square. And what is f of x? F of x is equal to tan inverse x. So that means derivative of tan inverse x with respect to x is equal to 1 upon 1 plus x square for all value of x where x belongs to real number.